7. Welcome to this week's science video. Now this week's science is all based on physics, but it's not only based on that, but it's based on this amazing object that floats around in some wonderful galaxy known as planet Earth. We live on it, but there's lots of interesting aspects to this that we're going to be looking into this week. So first of all, you're going to be looking at the time zones. Why is it different times on the planet? And how do we decide what time it is? And who decided way back, many years ago, that it should be different times? We're also going to be focusing on things that orbit our planet, anything that orbits any object, actually, any mass, and why it orbits, what forces keep it orbiting. And we're also going to be talking about when objects, masses fall to planet Earth, what's going on. So, are you ready for task 1? As always, practical investigation time. So, task 1, as always, is a practical investigation. You have two possibilities. The first one is you need to make your own parachute. Now you can use whatever you have in your house for this. It suggests using a little character. So I've got a selection here. I like to collect these, you know. You could throw squirrels to the ground and see if they land. You could throw whatever that is. I've got absolutely no idea what that is, but you could attach it to a parachute and, oh, here we go. Or, what about some fruit? You've got some fruit, or that one, funny thing. Or you've got an apple or a tangerine. You could attach a parachute to these. If you feel really up for the challenge, what about an egg? Now you could hard boil the egg, or you could leave it as it is. Your challenge is to look at all the factors that impact how you can slow this object down. Follow the instructions. Good luck. I can't wait to see what you create. Right, okay guys, task 2 involves a bucket and some water. So I've chosen to come outside for this. I would suggest you do the same thing. If you've got any sort of bucket, but you have to make sure that the handle is really secure. Now you put some water in your bucket. You can see the water in my bucket. Now we're looking at the forces that keep objects orbiting in a circle. So if you do this, please think of the safety aspects of this. That's why I say handle must be really secure in your bucket, because you're going to throw this bucket of water around in a circle and you do not want the bucket to detach from the handle. Okay, so what you're going to be careful, everybody out of the way. You have to be really confident about doing this, because I do not want freezing cold water on my head. So, you have to do this with conviction. That means you have to just go for it. I'm going to swing this bucket of water around my head, and the water is not, I can hear it sloshing, but it's not coming out. Woo! Phew! And that is the spinning bucket challenge. Good luck. Just a quick point about the bucket challenge. The force that you're seeing in action here is called a centripetal force. And that's the force that's meaning it can travel around a point. Now the force, the centripetal force in this example is my arm. I'm pulling the bucket in towards me as I spin it round. The centripetal force is provided by gravity for planets and for satellites going around other masses. So centripetal force is the one we're seeing here. Good luck! So task 2, as always, we're looking at a particular scientist related to all of this. This time, particular favourite because this guy's Scottish and he was born in Fife in Scotland. Sandford Fleming, many years ago. Read the information pack you've been sent to find out exactly when. He did move to Canada when he was 18, so in some things you'll read that he was Canadian, some he'll be Scottish. He was very much Scottish, and he decided that actually time zones around our world were very necessary to understand what was going on. So our planet does rotate on an axis, so some of us are in the dark and experiencing night, while some of us are in light and experiencing day. So he figured this needed to be looked at so that we could all talk about times of the particular day that would work out through the whole world. And so that's what Sandford Fleming did. He sorted this out, gave the world time zones, and decided on one particular place on planet Earth where that time would be the end of a day. And he put down the very middle of this map. He started off as calling that as the reference time, and I'll talk about this in the next task. And then if you go this way on our planet, you add time on, you go forward in time, and if you go this way, you go back in time. Now he had the international date line, which is a line where he said that was where the reference point of the time, there was a whole day difference. And again, I'll explain this in the next task, but that's over here somewhere. Now, my mum actually sailed across the international date line. And that means that you're jumping an entire day, because at some point on our planet, we have to catch up this whole day in terms of time. So if we meet my mum, first of all, this is my mum, and in fact this is my mum. She has been sailing around the world on a yacht for about the last 15 years. Many, many stories. This was her in the Galapagos with some of the Galapagos tortoises, and that relates to last week's task of Darwin. So she has been in the home of the Darwin thoughts. So this is my mum, and if we then look, this is her boat on here. Her boat is called Cat's Paw. That's a certain little creature having a sleep. When they sailed across the international date line, that was over here. They sailed, the international date line zigzags down here. They sailed between a tiny island called Nui and Tonga, and they were going this way. And when they crossed the international date line, it was 2:30 in the afternoon on the 2nd of October, and within a millisecond, when they crossed the date line, it became 2:30 on the 3rd of October. So they have never experienced the afternoon of the 2nd or the morning of the 3rd of October 2004. They do not have that. They do in their whole lives, they've missed that day. That's pretty special. So you'll read lots about Sanford and Fleming and his time zones in the pack. Please try and answer the questions. Good luck. So task 3, explanations. This is all about the key language associated with your explanation, and an explanation always gives a because. This happens because. Remember, that's the key thing when we hear the word explanation. The first one, I'm asking you to explain, why does everything fall to the ground, but why do some things fall slower than others? So there's a certain force that I'm sure we can all remember of why everything falls to the ground. It's a pulling force to the centre of our planet that's very strong. It's actually, though, a force that we can feel that every object has. Every object has this, or every mass has this particular force. And then we've also got a couple of other things to think about, which is the density or the mass of the object. That's going to affect how it falls. But the other aspect that's going to affect how it falls is its surface area. So if I take 2 pieces of paper, for example, and I crumple one up into a ball, it's the same paper. This one has a much larger surface area than this one. So another force that we can remember begins with air, resistance. That's going to have a part to play in how these 2 objects fall. It's a bit like the bowling ball and the feather. So if you have a look at them, these will fall very differently. I've got one that's floating and one that just fell. So have a think about the key language that you need to use in your explanations. Have a think of Newton's laws as well. Now, the second explanation I've asked you to provide is to do with these amazing things called time zones. Now, this is related to Fleming's work, and what he basically then calculated and what they found out and we now use today is if we take our planet Earth, there was 2 aspects of this that are really important in how we've now got a 24-hour clock and how we've got different times around our planet. Now, if you imagine taking a slice of the equator, so I just take a little slice out, I end up with a circle. And a full circle, as we all know, is 360 degrees. So that's the first thing we have to know to understand time zones, is that a slice through our planet Earth at the equator provides us with 360 degrees. Actually, it would be a slice through anywhere, but the equator is particularly important. Because then another thing we have to know, that of course our planet Earth is spinning anti-clockwise. And do you know that at the equator, it travels at 1,000 miles per hour every day, every minute of every day. That's the speed we are travelling now. So those two bits of information, the fact that we've got 360 degrees is all the way around our planet, and the fact that we are spinning at 1,000 miles per hour. If you do the maths and the calculations, that means that we spin 15 degrees every hour. So every hour, the Earth moves by 15 degrees. Now there are 24 lots of 15 degrees in what we now have as our 24-hour day, or what we have as our 24-hour day. So that's how we got these particular dimensions and bearings on this graph, or degrees on this graph. If you come and have a look at this map, this is basically our planet Earth flattened out. Now, because of where we live, we are in the middle of this map. Of course, other countries can be in the middle of their own map, but it doesn't change things for time zones. If you take a look down here, Greenwich Mean Time was what Fleming said was the reference point for time, and that is at 0. And then if you go 15 degrees this way, we have a mark, and then 30 degrees, and then another 15 degrees, we have 45, and these mark our time zones. Now if you go back to 0 in the middle, we go this way, and it goes 15 degrees west, then 30 degrees west, and 45 degrees west. If we zoom back out and have a look at the whole map together, we then have these points marked at the bottom, and what Fleming said was at 0, this going straight up here, and that lines up with us at Greenwich Mean Time. This is our reference point. So that's where, if you like, all time is referred to and from. So if it is a particular time at us in London, if you go 15 degrees this way, you add on 1 hour, because we have now gone into the first time zone. So 15 degrees is one time zone. So we add an hour if we go this way. If you then go another 15 degrees, you add another hour. And you keep doing that until you get right over to here, where you've added 12 hours on. So that's where you see, so my mum right now, I would love to have done a video call with her, with you, for her to tell you about her crossing the international date line, but she, right this second, is hopefully on a flight from Bangkok trying to get back to the UK from where their boat is. And the time in Bangkok right now is GMT plus 7. So that means it's 7 lots of 15 degrees from Greenwich Mean Time, from this prime meridian, this line that goes right up here. They're imaginary lines, they don't exist as real lines, but they help us with time zones. Now if we go this way, we also have 15 degrees, then 30, then 45. But what do you think happens with time? If we add hours going this way, we're going back in time zones, and so we take 1 hour off, then we take 2 hours off, 3 hours off. So you can have GMT minus 5, for example, if you live somewhere in Canada. So that's how the time zones work. We obviously have our international date line, because if we go back 12 hours, and then from here, if we go forward 12 hours, that's a whole day. So the people here and here are now on slightly different days. Now, what's really interesting is that the international date line, which is the edge of this day that we've managed to map out on the world, it's a zigzag line, because we do not want to give half a country one day and half a country's an entire day ahead. So what they've done is the international date line zigzags through from the top here. It's exactly opposite us, opposite the prime meridian, Greenwich Mean Time, and it zigzags here and it weaves its way through these countries. It goes in a straight line, weaves its way across here and back down. So that is the international date line. Now some countries have decided, for example like China, they do not want, because some of China, of course, is in one time zone and some of China is in a different time zone. They've decided they don't want some of China to be at a different time of the day than the rest of China. So all of China have chosen and have decided they're on the same time zone. Whereas the United States of America, they cover 6 time zones. So depending on where you are, and it's these imaginary lines, depending on where you are, you could be several hours ahead of other people that live in the USA. So that's a quick whistle through a really complicated topic of time zones. So task 4 is looking at the amazing and incredible scientific endeavours of Felix Baumgartner. Now he, a few years ago now, I will never forget the day he was doing this, because we could watch parts of it live, which were incredible, but he decided to send himself from planet Earth, and he got himself up with a hot air balloon, an incredible scientific and technology and engineering, and he came to 39 kilometres above the Earth's surface. And what he then did was, there's a video you're going to watch, this is other videos, he then was in an amazing, more than a spacesuit. You'll see it, please do watch the videos. He then free fell. He took several world records with this incredible flight that he did. But he then free fell from this balloon down to planet Earth and then pulled a parachute towards the end. So the force of gravity brought him to the Earth's surface, but my goodness, did it bring him quickly. He actually set 3 world records on this incredible day. One of them was the highest free fall. Another one of them was that he is the only human being to travel faster than the speed of sound, which is extremely fast. There were times during his flight where everybody back at the control centre were very worried because he went into a spin. Please watch what he did. It is phenomenal, slightly mad, I have to say, but incredible. He went up to the Earth's stratosphere. So there are 3 layers. He went into the middle layer, which you'll know a lot of you as the ozone. He was right up where 90% of the ozone is. That's where he took this flight from, and he plummeted to the Earth. Please try and summarise what he did. Take a look. It is incredible. Enjoy watching it and enjoy making your own notes. Good luck, Year 7. Oh. Right, here we are. We've got these 3 little nutters. They're all doing so well. They have no idea where they live on planet Earth. To them, time is all about when they get some milk and when they get fed. So that's what's important to them. They are now 4.5 weeks old. They can hear really well, they can see really well, and they can certainly walk about really well. Do you want to come and see the world? Do you want to go travelling? There we go. Thank you, Year 7. Keep up the fantastic work. You are doing incredibly well. Good luck.